This aluminum can is not the end of a product. It is a reusable resource that can return again and again. Recycling aluminum is one of the fastest industrial loops on Earth, turning waste into new metal with astonishing efficiency. But the loop only works when real machines separate, clean, and remelt scrap into controlled, usable material. What looks like simple melting is actually metallurgy, chemistry control, and a constant fight against metal losses.
Today we follow the full chain: can to scrap, scrap to slab, slab to rolling, and rolling back to cans.
This process matters because energy is the real currency of modern industry, and aluminum recycling spends far less of it. Aluminum can be remade without losing its basic identity if contamination is controlled and processing is disciplined. The story starts in a bin, but it ends inside massive furnaces and rolling mills that reshape metal at scale.
Every stage has a purpose. Sort correctly, remove coatings, melt cleanly, cast precisely, and roll consistently.
If one step fails, quality drops, losses rise, and the circular promise becomes expensive and unreliable.
Watch closely. A thin can becomes a heavy slab, then becomes a thin sheet again, without magic, only engineering. We will stay realistic and detailed, showing what plants actually do to protect workers, equipment, and product quality. No background music, just the real sound of industry, while the narration stays calm, technical, and clear. By the end, you will understand why recycled aluminum can save enormous energy compared with producing primary metal. And you will see why the word infinite is a goal in quality, not a claim of zero losses. When people say aluminum is infinitely recyclable, they mean the metal can be remelted without losing its fundamental structure.
Unlike many materials, aluminum does not downcycle by chemistry. The challenge is contamination, oxidation, and process control.
Every time scrap is heated, oxygen trying to steal atoms at the surface, forming oxide that becomes a key source of loss.
So recycling is not just reuse. It is controlled remanufacturing that protects metal quality while limiting waste. Plants measure and adjust composition because packaging alloys must meet tight tolerances for strength and formability.
In practice, the loop is nearly endless, but it is never perfectly lossless. Small percentages become dross and residue.
Shredded scrap melts faster, but the increased surface area can increase oxidation. Engineers balance speed and yield. Even one wrong contaminant, like trapped moisture or mixed metals, can create defects or dangerous reactions in the furnace. This is why the earliest steps, collection and sorting, decide whether the later steps will be efficient or costly.
Quality control starts early and continues through melting, casting, and rolling, so the final sheet behaves predictably.
The goal is simple: produce a clean, controlled melt that can be cast into a new starting form for rolling.
From here forward, every action aims to reduce losses, prevent defects, and keep the process stable and repeatable.
The sound and heat are real, and so are the risks. Safe handling and dryness are non-negotiable near molten aluminum.
With the basics clear, we now follow the real industrial path, from bins to bales, and from bales to clean scrap.
This is the hidden infrastructure behind the word recycling, where the loop becomes a measurable industrial system.
The journey begins with collection, but what matters is what arrives at the sorting plant. A mixed stream, not pure metal.
Material recovery facilities separate recyclables using speed, physics, and relentless repetition across conveyor lines.
Steel is removed first with magnets. Aluminum is not magnetic, so it continues forward to the next stage.
An eddy current separator creates a changing field that pushes non-ferrous metals like aluminum into a different path.
The cleaner this aluminum stream is, the less waste forms later in the furnace, and the higher the metal yield.
Humans still matter. Workers remove bags, food waste, and odd contaminants that machines cannot catch reliably.
Once aluminum is concentrated, it is compacted into bales for transport, lowering handling costs and stabilizing the feed.
Baling also helps plants meter material into shredders and furnaces with predictable mass flow and fewer jams. But bales can hide problems: trapped moisture, mixed metals, and plastics that will burn or contaminate later. This is why quality checks continue, even when the stream looks clean at high speed. From the bunker, aluminum moves towards size reduction because small pieces melt faster and more consistently.
Every step here is about controlling variability, because variability becomes expensive when metal reaches high heat.
Now the bales are opened, and the scrap becomes a moving, noisy river headed into the shredder. Shredding increases efficiency, but it also increases surface oxidation risk, so downstream controls become crucial. Next, we remove coatings and moisture, because molten metal does not tolerate surprises. Shredding turns bales into small pieces that melt faster, but it also increases the surface area where oxidation can occur.
These curled fragments are used as beverage can scrap, and their thin walls demand careful handling to avoid excessive losses.
Air separation and screening remove light contaminants and control particle size, improving furnace stability and efficiency. Plants often add a final magnetic cleanup, because stray steel can damage equipment and contaminate the melt.
Next is one of the most important steps: removing coatings, inks, and lacquers that would otherwise burn in the furnace. A decoating system heats scrap so organics break down and are captured, reducing smoke and improving metal recovery.
Exhaust gases are treated, often burned in a controlled way, so emissions and odors are reduced before release. This step also helps drive off moisture, because water contacting molten aluminum can cause violent steam explosions.
Dry, clean scrap is safer to charge and creates less dross, improving yield and protecting furnace linings.
Operators monitor temperature and flow, keeping the scrap hot enough to clean, but not so hot it oxidizes excessively.
After decoating, the scrap moves directly to melting, so it does not reabsorb moisture from ambient air. Dust systems run constantly, because fine aluminum particles are both a health hazard and a potential fire risk.
Quality checks here are simple but critical. The cleaner the surface, the easier the next stage becomes.
Now the scrap is ready to become liquid metal, and we enter the hottest part of the loop. What happens next is controlled melting, where chemistry and cleanliness decide final product performance.
In the furnace, aluminum melts into a bath, but the process aims to protect metal quality and reduce oxidation losses.
Molten aluminum forms an oxide layer instantly in air. Plants manage this with careful charging and atmosphere control.
Dross is skimmed because it contains oxides and trapple metal. Reducing dross means higher yield and lower waste.
Fluxes can help separate impurities and coalesce inclusions, making the melt cleaner for casting and rolling.
Degassing reduces dissolved hydrogen that can create porosity in cast metal, harming surface quality and strength.
Sampling is constant. A small test piece tells operators whether alloy chemistry is within target limits.
If chemistry drifts, corrections are added, because can sheet must form smoothly without tearing or cracking.
The melt is then transferred carefully, because turbulence can pull oxides into the metal and create defects later.
Refractory linings protect the furnace, but they also influence heat loss, so maintenance affects both safety and efficiency.
Dross handling is messy but essential. It is a visible reminder that recycling is efficient, yet never perfectly lossless.
Temperature control matters. Too cold and you lose productivity. Too hot and oxidation and lining wear accelerate. Safety checks continue, because any moisture near molten aluminum can flash to steam and eject metal violently. Extraction hoods keep air cleaner, capturing fumes and smoke while maintaining a stable working environment. Now the melt moves toward casting, where liquid becomes a precise starting form for rolling.
This is the moment scrap becomes standardized metal again, ready for the heavy machinery of the mill.
Casting turns liquid aluminum into a slab, the thick starting form used to roll sheet and coil for packaging. Direct chill casting uses water-cooled molds, so a solid shell forms quickly, while the slab is withdrawn continuously. Cooling must be controlled, because uneven solidification can create internal stresses and surface defects.
Water management is constant here, with channels and spray patterns designed to stabilize temperature gradients.
Operators watch surface quality closely, because small casting defects can become long streaks after rolling.
After casting, slabs are cut to length and moved carefully, because they are heavy, hot, and still cooling internally.
Next comes surface preparation. Scalping removes a thin layer to eliminate segregation and improve rolling performance.
Those chips are valuable metal too, and they are collected for remelting as part of the same internal loop.
Edge and surface control now reduce the risk of cracks, edge splits, and surface marks in the hot mill.
Quality inspection is physical and practical. Flatness, surface integrity, and consistent dimensions.
Only after the slab is ready does it move to preheating, which prepares the metal for plastic deformation in the mill.
Preheating makes rolling easier, but overheating increases oxidation, so temperature is tightly managed.
This stage is where recycling looks like heavy manufacturing, because the goal is precise, repeatable sheet production. Now we enter rolling, the step that turns a thick slab into kilometers of thin strip. What follows is force, heat, and speed, controlled so the final sheet stays uniform and formable. Hot rolling begins as the preheated slab travels on roller tables toward the mill, glowing with stored heat. Before heavy reduction, descaling sprays remove surface oxides so defects do not get pressed into the strip. A reversing mill squeezes the slab repeatedly, each pass reducing thickness and increasing length under controlled force.
Roll surfaces, coolant, and lubrication matter, because friction and heat shape both thickness and surface quality.
As the strip lengthens, guides and tension control keep it centered, preventing edge damage and shape problems.
Operators monitor the line constantly, because a small instability can become a major defect across an entire coil.
Edges are trimmed to remove cracks and irregularities, and the trim is captured for recycling back into the melt.
The hot strip is then coiled, turning a long ribbon of metal into a transportable form for the next process steps.
Cooling rates influence microstructure and flatness, so sprays and airflow are managed along the runout table. At this point, the metal is already sheet-like, but it is not yet at final gauge or final surface finish. The coil is moved carefully because dents and edge hits become visible defects after cold rolling. Hot rolling is the fast, heavy work. Cold rolling is the precision work that finalizes thickness and surface. Now we shift to the colder, cleaner part of the mill, where tight tolerances define whether can making succeeds. From here, the process becomes quieter but more exacting, because tiny variations matter at thin gauges. Next, we reduce thickness further and prepare the sheet for the demanding forming steps of modern can lines.
Cold rolling starts by uncoiling a hot rolled strip and passing it through rolling stands that reduce thickness precisely.
Multiple stands can work in sequence, producing uniform gauge while keeping flatness and shape under control. Sensors track the strip continuously, guiding adjustments so thickness stays consistent across the width and length. Coolant and filtration protect roll surfaces and prevent heat buildup, which would distort tolerances and surface finish.
After cold reduction, the metal is stronger but less formable, because rolling work hardens the structure.
Annealing restores formability by allowing the microstructure to relax, which is essential for deep drawing and ironing. After annealing,
Finishing passes refine surface and flatness, preparing the sheet for high-speed forming lines. A light skin pass can improve texture and handling, helping the sheet feed reliably into presses.
The sheet is then slit into coils sized for specific equipment, because can plants need consistent widths.
Edge quality matters here, because burrs can cause tears, jams, and safety risks in later forming operations.
At this stage, the product is can sheet, thin, clean, and controlled to perform under extreme forming speeds.
Finishing is about removing variability, because variability becomes scrap when machines run at thousands of units per minute. Coils are packaged for transport, and every dent or scratch avoided now prevents defects on finished cans. Next, we follow the sheet into can manufacturing, where rolling becomes packaging in seconds. The metal is ready, and the next machines will reshape it faster than most people imagine.
At the can plant, coils unwind into press lines where sheet becomes parts at astonishing speed and precision.
Blanking punches discs, then forms cups, creating the starting geometry for the can body in milliseconds.
The draw and iron process stretches those cups into tall cylinders while thinning the walls to save material. Trimming makes every body the same height, and the ring scrap is captured to return to recycling loops. Cans are washed because cleanliness is essential for coatings, corrosion resistance, and safe packaging performance.
An internal coating protects the beverage from metal contact, and the can from corrosion over its life cycle.
Drying and curing stabilize that coating so it survives filling, transport, and handling without flaking or cracking.
Decking reduces diameter near the top, saving metal in the end while keeping strength where it is needed. Flanging forms the rim that will later be sealed, creating the interface for a reliable seam. The can end is made on a separate line because it needs different forming and strength characteristics.
Tabs are attached mechanically at high speed, and the end is scored so it opens predictably without failure.
Finally, seaming joins end and body with a tight mechanical crimp, creating an airtight seal for distribution.
This is where sheet becomes packaging, and where small quality issues become visible at scale immediately.
When everything is controlled, the can returns to shelves, ready to be used, and eventually recycled again.
Now we step back and quantify why this loop saves so much energy compared with primary aluminum production.
Primary aluminum from ore required breaking strong chemical bonds using huge electricity, so energy becomes the dominant cost.
Recycling skips most of that chemistry and focuses on remelting, which is why energy demand can drop dramatically.
This is also why recycled content often reduces carbon footprint, though exact savings depend on regional power sources.
But savings are not automatic. Plants must run efficiently, manage heat loss, and keep scrap streams clean and dry. Every contaminant increases waste, downtime, and defects, turning an efficient loop into a costly sorting problem.
Oxidation creates dross, and dross is where metal is lost, so good process control protects both yield and economics. Collection rates matter too, because the best recycling system cannot work without enough clean material entering it.
Safety is part of efficiency. Moisture control prevents dangerous steam events that can damage equipment and harm workers.
Modern recycling also relies on emissions control systems, balancing productivity with air quality and compliance needs.
When the loop runs well, it becomes a scalable form of circular manufacturing, not a symbolic gesture.
The can you recycle today can return as new packaging, because the material itself can be used again and again.
This is industrial realism. Heavy machines, strict controls, and a simple goal. Do more with less energy.
The more consistent the process, the closer recycling comes to that ideal of endless reuse at high quality.
And the lesson is broader. In a world shaped by energy and supply chains, efficiency becomes a form of resilience.
The loop ends where it began. A can back in the bin, ready to become metal again.